Okay, let's have a little look at inertial mass, which is what today's lesson is about. And this sort of carries on from Newton's second law, this idea that force is equal to mass times acceleration. So to talk about inertial mass, we need to have a concept in our heads of what inertia actually is. So inertia is the current state of an object. If something's moving, it's going to stay moving unless we do something about it. And if it's stationary, it's going to stay stationary unless we do something about it. This links back to Newton's first law, right? So let's think about inertia as the desire of an object to do what it is currently doing. They're quite happy as they are, and you're going to have to put in some effort to make them change. Things that are stationary want to stay stationary, things that are moving want to stay moving. Obviously objects don't want stuff, but that just helps us visualize and think about what's happening there. That basically can lead into this idea of how mass is linked to force and acceleration, which gives us sort of the logical idea that larger objects, those that have more mass and therefore more weight, are going to take more energy to move. This boulder here, call that A, is 5 kilograms. This boulder here is 10 kilograms, and hopefully it's clear that the 10 kilogram boulder is going to take more force to get it moving. We need to overcome its inertia, its inertial mass of 5 and 10 relatively, because it wants to stay stationary. This is all part of Newton's second law, that force is equal to mass times acceleration, and that mass is what Newton was talking about. He was talking about the inertial mass when he came up with this law. So the inertial mass is just equal to the force divided by acceleration. Kind of an example of this in play is this idea of a Shire horse pulling along a barge, if you look at the picture here. So this is how barges used to get moved up and down canals. Shire horses would pull them along. Now when the horse first starts pulling that barge, it's really hard. It takes a lot of effort on the horse's part to get it moving because the inertial mass of that barge is quite large. I don't know what the mass of a barge is, but it's probably in thousands of kilograms. So the greater the mass of something, the harder it is to get it to start moving. Now, once that horse has got the barge moving along, this bloke here can probably take the line and pull it himself because it's already got some momentum. It's lost some of its initial inertial mass. This works the other side as well. So that barge is going to be fairly hard to stop moving. It takes boats a long time to stop. You probably noticed when you're on the fast cat that they turn the engines off quite a long time before they get to the end of the pier because they have to sort of slowly slow down and coast in. So the greater the mass of something, the harder it is to start it or stop it moving, and therefore it's going to take more force. So it links us back to this idea mathematically here, right? We can link this as well to Newton's third law, which tells us that every action has got an equal and opposite reaction, and so for a difference to happen we need to overcome that opposite reaction. So for this guy here to push the wheelbarrow up the slope, he needs to overcome the inertial mass of the wheelbarrow. As he pushes it, it's going to be pushing him back as well. He just needs to overcome that pushback force of it. If the wheelbarrow is pushing back with a force of 5 newtons and he wants to move it up the hill, he's going to need to put in more than 5 newtons. So he puts in 15 newtons for a resultant force of 10 newtons upwards, right? Hopefully that helps a little bit. Hopefully that makes sense. A couple of questions and a bit of review in the form here. But just think of inertial mass as just the mass from Newton's second law, and think of inertia as the desire of an object to do what it is currently doing. If it's stationary, it wants to stay like that. If it is moving, it wants to stay like that. Okay, thank you.